Let's talk about the new JSON data type in ClickHouse. But first, let's start with the facts. ClickHouse is the fastest analytics database. According to open benchmarks like ClickBench, ClickBench contains about 50 different database systems with the results contributed by their creators or community, and ClickHouse is the fastest among production-grade analytics databases. Let's talk a little bit about what makes ClickHouse the fastest analytics database. First of all, it has a true column-oriented storage. So when we create a table, like in this example, with a few columns, the columns will be stored separately in separate files on disk, typically. And when we do a query, select query, ClickHouse will read the required columns, and ClickHouse will analyze this reading across the ranges inside the data. And ClickHouse will process all of this in parallel using different CPU cores. It will create a data pipeline, query pipeline, utilizing all the available resources. So the data is processed in parallel by many CPU cores. And on each CPU, we will also use the corresponding instruction set of the CPU using SMD instructions. When we have more threads, we will use more streams and process data even faster. Okay, now the question is not a question, another fact. ClickHouse now is the fastest analytics database on JSON. Let's take a look. What is the new data type? How to use it? And the new data type is very easy to use. You just create a table, you define a column with the data type JSON. As easy as in this example. The table can literally have just a single column of the JSON data type. But first, let's take a look at the example how not to implement a JSON data type. How not to do it. For example, we could store all JSON objects as strings. Then these objects will be in just a single file on disk. But when we do a query, when we read a key from JSON, it will have to read all these objects from disk. It will have to parse these JSON objects on the fly, and only then do the calculations like calculating aggregate functions or filters. And it is not fast, because it has to transfer data from disk or from external storage. It has to parse this data. So we should not do it trivially like in this way. We should do something smarter. We have to implement true column-oriented storage for JSON, like we do for regular columns. But JSON data is semi-structured. So we have to analyze our objects. We have to somehow deconstruct them to store efficiently. But if we do it, maintain the same query performance like on separate classic data types. Let's take a look how is it possible and if it is even possible. So let's take a look at the ideal example. If we store every key from JSON, A and B, in a separate file, we will achieve the same performance as with separate data types. So maybe we just have to store every key separately, analyze their data types, and it will be enough. Maybe. Then we will use the same parallelism, the same CMD instructions. Everything will be processed efficiently. But there are some challenges. The challenges are that if we define a table with explicit data types, we can have only a single data type per column. Like in this example, column 1 with int64, column 2 with nullable string, column 3 with array of int64. Then it will be stored in separate files, and for some data types, they can be stored in a few files. Like for arrays, we have one file with values from all of these arrays, and another file with offsets inside the column, actually with array sizes. For nullable, we have the data file and the file with null mask. But if we do it for JSON, there could be a case when our JSON object will contain a lot of different keys, like unbounded number of different keys, maybe thousands, maybe even hundreds of thousands different keys. And somehow we have to overcome this challenge. We cannot just store thousands of different files. The second challenge is that JSON objects can have different types of the same keys in different objects. Like we have an object where the key, sometimes it is an integer, sometimes it is a string, sometimes it is a nested subobject. And another challenge is that some keys could be sparse. Like they could be present once every million of records, and we still have to store them. But we don't want to waste memory, we don't want to waste on disk storage. We don't want to pretend that it is present a million out of million times. Okay, so what will happen if we store every key separately? Nothing good will happen. You can see it. We don't want this. We don't want a lot of files. What about different types? Let's take a look at this picture. So we have key A with integers in the first 3 records, with a string in the subsequent record. And then we have an array value in another record. And how to unify these data types? If we want to unify them, we cannot store it as an integer. We can store it as a string. We can serialize everything as a string, but it would be inefficient. And if we do it, we will lose the information about the original data types, and we want to keep this information. So we have to do something smarter. And these keys could be sparse. Like in this example, the key C happens is present only like just a few times across all the data. So let's take a look. Here is the traditional storage for fixed columns. Here are our 3 challenges that we have to solve. And the first solution is another data type named variant. So we have not only the new JSON data type, but also the new variant data type. And it looks like this. You type variant, and you write the options, different options as parameters. And this data type can represent any value of any of the specified data types. So you can insert integer in one record, string in another record, array in yet another record. And also, variant gives you support for nulls for free. So the value can be also null. Let's take a look how it is implemented. From the storage perspective, it will store every possible data type as a subcolumn in a separate file. So there will be 3 files, and for the array, actually there will be 2 files, because the array data type requires 2 files to store it. So 4 files in total, and actually there will be another 5th data file containing named discriminant. The discriminant will describe which of the data types every record is. It will index these data types starting from 0. So the option 0 will point to integer, the option 1 will point to string, the option 3 will point to array. And we have reserved number 255 that just designates nulls. Okay, so it's pretty simple. And in memory, we will also have offsets in every subcolumn. So when we want to locate, when we want to read the third record, like in this example, we will look at the third record in the discriminant, then go to the corresponding subcolumn, like this integer subcolumn, look at the offsets, and read the value at the corresponding offset. It's pretty easy. And we have our challenge to solve it. Now we can store different data types without unification. We don't have to convert different data types to a single data type. We use variant instead. Okay, and also our data files are not sparse. They contain only the records that are present. We don't store empty values. So if some value of some data type is infrequent, these column files will be short and small. And we also solve our challenge 3 in this way. So using the new variant data type, we solved 2 out of 3 challenges already. And it's really nice. And another component for the implementation is yet another data type, named dynamic. So we have 3 new data types for you: JSON, variant, and also dynamic. What is dynamic? It is similar to variant, but it does not. You don't have to specify explicitly the list of possible data types. The dynamic data type will automatically figure out which data types you inserted, and it will track the data about all of them. Let's take a look how it works. It works very similarly to the variant data type, but it contains another data column, data file on disk, designating which data types are actually present. And this set of data types can be different in different insertions in different data parts, and the dynamic data type will automatically figure out the full set of all possible options. And the question is, what will happen if there are too many different data types? And when there are too many different data types, actually we will stop creating separate files for them, and we will put the data into shared subcolumn named shared variant. It will record all the rest. The popular data types, like the first 100, will be stored separately, and the rest will be stored in a shared data file. So it keeps the balance between the number of files and efficient storage, efficient reading of the data. Let's take a look how it works. So we have a column with integers, strings, arrays, and the integer will go to the first file. The string in the second record will go to the second file, array to the third file, and then if the limit is 3 for the maximum number of types, the rest will be stored separately. And we have solved the first challenge, too many data types. Actually, we have solved just half of the first challenge because there is another problem. Let's take a look. And let's take a look how it works from the user perspective, the new JSON data type. You can use it as simply as in the first example. Just create a column with type JSON. But also you can specify optional parameters to customize this data type, like in the second example. And we have a parameter for the limit on the maximum number of different paths inside JSON, different unique paths. The maximum number of different data types in a single key. Then we can specify explicit data types, like type hints, for some path if we want. And then for this specific data path, it will not analyze data types. It will just assume the specified data type. And we can skip part of the JSON if we don't want to store the data. Like if you know that part of JSON contains like some encrypted data and you don't want to store it inside ClickHouse, or PII data, just skip it, and you can skip by regular expression. So it's pretty handy. Let's take a look at how it works when the number of dynamic paths starts to grow over the limit. By default, the limit is 1024. And the limit on the maximum number of types by default is 32. Okay, here are our parameters. And let's again look at the example. So let's suppose we have a JSON with the maximum number of dynamic paths equals to 3. In the storage, the key a.b will go into a subcolumn, into a file on disk. The key a.c will also go into a separate file. Then we have keys a.d and now it will be stored using the dynamic data type. And we have over 2 dynamic data types, so it will also contain shared storage. And so here is where it goes. And now we have another key, a.d.d. a.d.e. And it is over the limit. And actually it is still under the limit, but the key F is over the limit. And for this key, we just collect them into another shared storage for data path that did not fit into the limit. So it will work like this. The most popular case will be stored in a column format, column-oriented format, and the rest will be stored in a format similar to the row-oriented format. And in this way, we can actually store JSONs with unlimited number of keys. The question is it fast? And I spent so much time explaining these boring details, so you should think that it must be worth it. It must be fast, right? Let's take a look. And to check it, we created another open source benchmark, publicly available, reproducible, named JSON Bench. And we already received a lot of contributions for other open source databases to this benchmark. We have tested a few databases with the native support for JSON by ourselves, but then received some new contenders. And it is not surprising that ClickHouse is the best. What is surprising? You can look at this chart. And it has logarithmic scale. So Postgres is thousands times slower. Let's take a look at, it is not surprising, right? No one will be surprised that MongoDB is slow, especially if you know about ClickHouse. And by the way, ClickHouse is the only system that does not do type unifications for different data types. It does not have to convert data types to the common data type. It does not even assume that the common data type exists. It will store information about the original data types. So it is not only the fastest analytics database for JSON, it is also the most accurate. It can reconstruct the original data without any information loss. And everything else does not do it, and will lose some data from JSONs. Let's take a look at some comparisons. So first of all, let's compare with MongoDB. And MongoDB is the database for JSON. It was created to do a variety of stuff with JSON. But you know what? If you do analytics, ClickHouse does it better, and not just better. So when MongoDB spends over 15 minutes, ClickHouse will spend 400 milliseconds. So when you do a query in ClickHouse, you press enter and you receive the result immediately. When you do it with MongoDB, you will have an impression that either MongoDB breaks or your internet connection is broken or something wrong about our universe.
Is most of the performance from I/O or compute?
Both. So, well, there is performance difference from the I/O perspective, because ClickHouse will read only the required files on disk containing subcolumns, containing compressed subcolumns. But also it will process this data efficiently because it will use SIMD instructions. It will use vectorized query processing to process exactly these subcolumns. And MongoDB will have to read all these JSONs every time. So ClickHouse is 2,500 times faster. But it is not only faster, it is more storage efficient. When let's do this comparison. We will use the same compression algorithm in MongoDB and in ClickHouse, ZSTD. But the same data set will take 147 gigabytes in MongoDB and 40% less, just 92 gigabytes in ClickHouse. And by the way, the data set is 1 billion JSON documents containing events from the social network named Blue Sky. And these JSON documents are quite complex. They contain a lot of nested fields with unlimited nesting, but actually among these billion documents, the nesting was like 20 times, 20 levels of depth. Okay, and you might guess why ClickHouse is more storage efficient. Because it will compress not the whole JSON, but it will deconstruct the JSON and compress it by components. And what is also surprising, or maybe it is not surprising after everything that I presented, that if you just take this data set of JSON documents in JSON lines format and compress with the STD, and if you put it into ClickHouse, and ClickHouse will also use the STD compression, ClickHouse will do it, will use 20% less disk space. So ClickHouse is not only the fastest database for JSON analytics, it is also the best way to compress JSON data. So if you want the best compression for your JSON, just insert into ClickHouse. And yes, if we compare to other databases, ClickHouse is the most storage efficient. Like Postgres took 600 gigabytes. It is 600 bytes per one document on average. ClickHouse took 92 gigabytes or 92 bytes per document. And no database comes close. We can see like the best contenders are Victoria Logs, GrabTimeDB. They are specialized databases for logs written in Rust, another in Go. And ClickHouse is analytical database, almost general purpose analytical database. Let's take a look at another comparison. Let's look at a single query among this data set that does aggregation across 1 billion JSON documents. And not only ClickHouse is the fastest with sub-second result, it also takes only less than 3 megabytes of memory to run this query. MongoDB takes 16 minutes, so I don't even want to know how much memory does it use. Elasticsearch gives the second best result, but with 5 seconds, it is like 10 times slower. And if you try to compare with DuckDB, don't even try. DuckDB will spend more than 1 hour for the same query. And similarly, Postgres is not an analytical database, but it does have native support for JSON, so we expect at least some performance from it, but it did not meet expectations. Okay, so ClickHouse now has the new JSON data type. It gives true column-oriented data storage for semi-structured data. It gives the most storage-efficient data format. It is easy to use. You don't have to do any customizations. By default, just write create table, your column, JSON. You can create indexes on this JSON column. You can use it as you can use subcolumns as a primary key. The SQL language is also very easy to use. Just use the dot notation and array subscripts, and it will work in a natural way. It is thousands times faster than traditional data stores for JSON. And since the latest release, 25.3, which was released 2 weeks ago, it is production ready, it is generally available. So install the latest release today. Try the new JSON data type. And thank you for listening. Yeah, please.
All right, I'm going to be slightly critical, but I think you're going to have a good answer. Can you go back to the slide where you talk about the amount of memory you use?
Yeah.
So in doing this comparison, what you don't specify is your reference hardware architecture. That's all right. So this is probably a null question, but since you're using so little memory, which is a great thing, is it possible that the comparative long run times are being caused because the reference architecture doesn't have enough memory and you're getting an excess amount of page faults?
It is possible. By the way, the first question about the machine types, it is documented on jsonbench.com. So you can go to this.
Can you tell us if the reference architecture had enough memory such that you're not comparing apples to oranges in terms of was DuckDB and Postgres, do they generate a large number of page faults which can just absolutely grind performance?
It is possible, but it should not happen because this query does not require pulling all this data into memory. It can go in a streaming fashion, so it can load some chunks, process these chunks. So.
Two things. When is it in ClickHouse Cloud, so I can use it? And then the second is the insert speed. Like if you're creating all these files on disk and all this, I buy the query performance is speeds is very, very good. But is it slowing down insert performance?
The first question is when it will be available in ClickHouse Cloud. Actually, it is available even today. So by default, you use in ClickHouse Cloud, which is currently 24.12. And you need a newer version for the JSON data type. But you can select the fast channel in ClickHouse Cloud. And then you can ask specifically to enable the new JSON data type, and it will be enabled for you. We have a lot of customers already using the new JSON data type in ClickHouse Cloud, even before it was in GA. But today it is in GA, so it is even more encouraged to enable it. The second question is about insertion speed. If you compare the insertion speed, when you just insert JSON as a string inside a single column versus inserting into the JSON column. Yes, inserts will be slower because they will have to analyze and deconstruct this JSON and write more files. And the actual difference will depend on your data set. How big are your JSON objects? How many keys and nesting levels do they have? And it could be from just like tens of percents of performance difference to several times difference. Actually, it will scale as any other inserts. So if you increase the number of machines and do different inserts to different machines, you can scale it regardless of the speed.
Of all the different implementation details that you walked through and the challenges that you overcame, what do you feel like was the trickiest thing to solve in implementing this?
The most difficult part was to implement this fallback storage. that will take care of the rest of keys that don't fit the limit. Because this storage should contain some encoding about actual data types. And when we read the data, we have to do it from dedicated subcolumns plus this shared component. And it requires some care. Also, there was a challenge storing some, so the columns require some like prefix dictionaries and the data for every record. And the code that has to deserialize and read these dictionaries in advance and take care of this, it is actually not so simple. Yeah, please.
So you had one slide where you kind of walked through like an example JSON dataset and how all the files were created. And in that example, the most common paths got their own column files, right? I guess my question is, like, let's say beyond those first few documents, let's say, or yeah, first few documents, you get another like 1,000 documents where the schema completely changes. Does the engine, I guess, like reconcile and reorganize the columns dynamically?
Yes, this decision could be made during background merges. So you do one insert with one structure, and a certain set of subcolumns will be stored separately. You do another insert with completely different data structure, and another set of columns is selected. But then we have to merge these data parts, and during this merge, we have to make decision which subset from every part will be stored separately.
Hi, these are great benchmarks, but Elasticsearch is being used extensively by enterprises for e-commerce search, enterprise search, and observability use cases. Mm-hmm. So how do you think, ClickHouse holding up in that use case? Are you like very confident that these benchmarks will hold when the data sizes reach about a petabyte, 2 petabytes, 3 petabytes?
Absolutely confident. When the data size will reach several petabytes, Elasticsearch will be just not an option. I'm absolutely confident about this. If you want to find some current advantages of Elasticsearch, it will be text search, text indexes. Mm-hmm. But you have to pay for text indexes with increased data storage, and you will not get the same compression. In Elasticsearch, if you compare the data size to the source data size and just divide one to another, you will get negative compression ratio because it has to store a lot of extra data just to maintain these text indexes. And here you can see that Elasticsearch took 360 gigabytes, ClickHouse just 92 gigabytes. But it is not the only problem. Another problem is that Elasticsearch will require massive amounts of memory just to operate it.
Right. So, are you still very confident when it comes to observability use case, purely text logging based database for Elasticsearch for ClickHouse? Yeah, 100%. Because if you just list companies that do observability, list 20 or 30 such companies, and out of them, more than 90% have ClickHouse as a backend. There are a lot of migrations from Elasticsearch to ClickHouse, specifically for observability use cases. And you can read about the customer stories about these migrations in our blog, or just type into whatever Google migrations from Elasticsearch to ClickHouse, or ClickHouse for observability.
So I just wanted to follow up on the first question, which was about the benchmarking methodology, because obviously these numbers are crazy. encourage everyone here to actually visit jasonbench.com. We explain the methodology in detail. For example, actually, all of these benchmarks were run on identical EC2 instances, the M6i8XL to be specific. So there was 128 gigabytes of memory available to run the test. ClickHouse obviously used just a handful of megabytes, but I don't think we should have been running into any out-of-memory type scenarios with 128 gigabytes of memory, 32 CPUs.
Thank you. So this variant data type or variable data type, it's available as well, and not just JSON. And I was wondering, how hard would it be to implement our own, let's say we have our own encoding format, or maybe we use MessagePack. Like, would it be possible to kind of implement similar logic that you do with JSON using MessagePack, or using like flex buffers, something like that?
Do you mean using MessagePack inside ClickHouse or inside your?
Inside ClickHouse, yeah. So basically adding a new MessagePack data type. Let's say.
So MessagePack is a binary format for JSON, but it is a row-oriented format. So it just encodes JSON sequentially as it was. In this regard, it is similar to like Bison or somewhat similar to Avro, Apache Avro format. It does not really make sense to use it inside ClickHouse, but we do support importing and exporting data from MessagePack format, similarly how we do it for JSON.
Okay.
Thank you. I was wondering, coming from a traditional finance kind of space, do you see ClickHouse applied to live feed market data? Purely, I think it's purely, to my point of view, it's purely numeric, like numbers. And when you feed that through, let's say, New York Stock Exchange APIs, do you see that ClickHouse could optimize than other solutions, the current solutions on the market? Like,
yeah, we have these use cases for companies that do trading. For other finance companies, ClickHouse is quite popular in this scenario. ClickHouse has special data types for financial data, like decimal data types with high resolution. And this is not only about traditional fintech companies, also about blockchain, as you saw today.
that's amazing. Thank you.
We do have to wrap up so that the folks who work at Braze and in the building can leave, the security folks. Really appreciate everyone for coming today. Really appreciate all of our speakers. Another round of applause for everyone. Thank you very much. We have these events basically once a quarter, so look out for the next one on meetup.com. And then for anyone who's interested in speaking, do let us know. We always have great partners, great customers speak, but always looking for more. Thanks again, everyone.
Thank you.